We finished up determinants last time. In particular, we talked about some applications of determinants. In particular, we used Kramer's rule to solve systems of equations using determinants. We said that Kramer's rule was useful if you've got same number of equations as you have variables you're trying to solve for. If the system is small, right? If you've got like a two by two system or a 3 by 3 system, Kramer's rule is a pretty nice computational way to get your solutions relatively quickly. If it gets bigger than that, if there's lots of coefficients, then it's probably not the most computational friendly way to solve a system of equations. So you probably do a different method. Also, Kramer's rule doesn't work if it's not square, right? If you don't have exactly the same number of equations as you have unknowns. It also doesn't work if you don't have a unique solution. So it has advantages if you've got small systems, if you've got disadvantages if you've got non-square systems or systems that don't have the unique solutions. So we also talked about how you can describe equations of lines and equations of planes given 2 points for a line or 3 points for a plane using determinants as well, and how you can talk about using determinants to determine if 2 points are, if 3 points are collinear or 4 points are coplanar. So, in any event, talked about all those applications of determinants. So that was what we finished up with. We're going to switch gears a bit. We're going to come back to determinants later. But we're going to switch gears a little bit for the time being. Again, one to Declan for All right. So hopefully a lot of what we're going to talk about today looks familiar. Okay. So if you've had a physics class, if you've had Calc 3, most of what we're going to do today should look very, very familiar. Okay. So in any event, we talk about defining what we mean by a vector in Euclidean n space. So you're used to drawing pictures back in Algebra 1 class and going forward, where maybe you've got the Cartesian plane here, the Euclidean plane, and you've associated with some point in the plane, you've got an x coordinate and a y coordinate, right? Now, you've also talked about, if you've had physics or if you've had Calc 3, you've talked about that also this point can help you, I don't know why I put a y1 on there. That point can also help you define what we mean by a vector, right? So usually if a vector is in standard position, it starts at the origin and then you draw an arrow that goes out to that point, correct? So there's kind of two ways that you can think about that point. One way is just literally the point, right? It's the point xy. The other way is to think about it as the terminal point of a vector that starts at the origin. So there's a couple of different ways that you can think about that point. In Calc 3, you then bumped it up a dimension. Same idea though, if you've got an x-axis, a y, oh hey, drawing different than what you do in Calc 3. I've been teaching that static stuff and they put their axes in a different direction. Your x, your y, your z axes, and then again, if you've got some point x, y, z, again, that could talk about where that point is in space, or again, it could be, I'll put this in a different color, the end point of a vector, again, starting at the origin and going out to, or I should say the terminal point of a vector, starting at the origin and going out to the point x, y, z. Got a couple of different ways to think about it. This is about as good as we can do graphical representation if we've got a 2-dimensional vector or a 3-dimensional vector, but we can do this in any Euclidean space. Okay, so we use that boldface R that I'm sure you're used to using. We can also just think of the real numbers themselves as vectors if you would like. Again, if you think about the real numbers themselves as a vector, you're going to be, graphically, it would be on a number line. Dorian, you're going to want to hand out. So, okay. All right. Graphically, you can think about the real numbers being a number line. Again, your vectors then would start at 0, and then you would just have an arrow that goes out to wherever the endpoint is. So again, you can think about the real numbers also as being vectors themselves. The confusing part about that is that we're also going to use our real numbers as scalars here in a minute. Okay, so usually, though we we don't necessarily think of the real numbers as our vectors. We're going to think of those as our scalars and things that we're going to change the length of vectors for when we multiply by them. So, but in general, we can think of these as vectors as well. To emphasize that, typically we'll just put a little 1 on there. It's a one-dimensional vector space, and we'll talk about what we mean by dimension later on. So this would just be your set of real numbers, but again, thought of as vectors. What I drew over here on this side, this would be R2. So this is just a set of ordered pairs, again, thought of as vectors. And I should say, I'm going to say it's thought of as endpoints or terminal points of vectors. And then so on down the line. So we'll use this notation Rn, and a lot of times we'll just say this is n-dimensional Euclidean space. Or for a shorthand, we might just say Euclidean n space. So just so that we're all on the same page by what we mean by this notation, the tuples, again, we think about it. I personally don't like the notation. I'd rather, if I want the tuple to denote a vector, I'd rather have different brackets on the end of it. Usually I use pointing brackets on the end to denote a vector. So you might see me do that. It means the same thing. In any event, the tuple here is representing the vector. Again, the vector is going to think about it, start at the origin and go out to that point. When we talk about all the collection of all those n tuples, we can refer to that as Euclidean n space. And typically we'll just say Rn at that point. So you've dealt with R2 and R3 most likely in Calculus 3 if you've had Calc 3 or in physics class. Because usually try to keep things where you can actually see them. But there are Euclidean spaces for any dimension that you would like. Dr. Olson's husband works for a company that does satellite things, and they actually use 6-dimensional vectors to do different things for them. So I believe he's coming and talking to the AI class sometime in March. So should be a good talk. But I do know that he uses actually 6-dimensional vectors to represent things for satellites. So there are actual honest-to-goodness applications for vectors that are higher than 3 dimensions. Okay. In any event, let's talk about what we mean by addition and scalar multiplication. We've already talked about this graphically a little bit, especially when we were talking about trying to help us understand what a determinant function might actually do. We talked about what adding vectors looks like and what multiplying a vector by a scalar looks like. If we do that in 2 dimensions, which is typically the easiest way to see it, if I have the vector, let's just do it with points to start with. Say I have the vector 1, 2. That does not look like 1, 2. Doesn't matter. Don't really care. I just didn't want to use letters. And maybe the vector up here, that is 2, 5. My scale is really bad. Okay. Remember how we do this graphically, right? We just think about moving one vector. As long as I don't spin the vector, and as long as I don't lengthen or shorten the vector, I don't change the vector. I can move it wherever I'd like, and it's the same vector, right? So we think about moving this here, and then I can think about completing the parallelogram, right? And then doing the thing that's in the middle. It's a terrible picture that I have drawn right now because I've gone into the words on the screen. Right, so then the result would be what's in here, correct? And the way we add then is what? Well, to get to this point, I can think about first moving it in the x direction. The first vector moved it 1 unit in the x direction. The second vector moved it 2. So I must be 3 units in the x direction. In the y direction, the first vector moved it 2 units. The second vector moved it 5 units. So I must be at 7 in the y direction, right? And so that's how we add it. We end up adding it component-wise. And that's exactly how we're going to do it for n-dimensional vectors. So if I have x1, x2, x3 out to xn, and I want to add it to y1, y2, y3 out to yn, we'll add those two things together just by adding components. We'll do it component-wise is typically how we say that. So when we add these two things together, we just add components together. And so I add the first components, the second components, the third components, and so on, so on down the line until we get to the nth components. So it's just a natural extension of what you do for 2 dimensions and 3 dimensions. Same concept, right? So we do scalar multiplication, same idea. Let me see if I can draw this a little bit better to scale. If I have the 1.12 and I want to multiply that by 3, then I would make that vector. I'm not going to change. If I multiply by 3, I'm not going to change its direction. But I would make it 3 times as long, right? And so again, we notice that if I want to make it 3 times as long, I need to make my x coordinate 3 times as big and my y coordinate 3 times as big. So the effect of making it 3 times as long is to multiply each component by 3, which is exactly then how we extend our definition of scalar multiplication. So if I have a constant c times a vector in Rn, that's just going to be cx1, cx2, cxn. My guess is many of you have already seen this stuff. We're just extending it to n dimension. Yeah, DeMarcus.
So what about scalar multiplication when you times by reciprocal? So say you just do about 1/3.
Same idea. You just multiply each of the components by a third. Yep. Same concept.
And the negative as well.
The negative as well. Yeah. So then the negative would just make it point in the opposite direction. Yep. It's just harder to visualize that if you get above 3 dimensions. Yeah. But it's the same idea. All right. So, yes.
What's the C doing? What's the C doing?
What's the C? That's the scalar. That's the real number that we're multiplying by. So it's lengthening or compressing the vector by that length, by that number. So if C was 2, it'd make it 2 times as long. If C is a third, it'll make it a third as long. If C were -3, it'd be 3 times as long, but in the opposite direction. For this purpose, yep. Okay. All right, so just make sure that we're all on the same page with the computations. And then we'll talk about some properties of these vectors. The whole idea why I'm going through this a little bit more slowly today, even if you're familiar with the stuff, is because we're going to change things up a bit, because of course we do. Okay. when we get to the next section. All right, so this says to do u plus 3v. Which thing do you think you're going to do first, the addition or the multiplication? The multiplication, right? In particular, trying to take u and add 3 doesn't make any sense, right? That's a scalar and a vector. I can't add a scalar to a vector. Okay. So when we do this, I'll do the 3 times at first. So I've got the vector 4, 2, negative 1, 1. The first thing we'll do is we'll distribute the 3 through. So take that 3, multiply it through, get negative 3,099. And then add component-wise. 4 minus 3 is 1. 2 plus 0 is 2. Negative 1 plus 9 is 8. 1 plus 9 is 10. Like I said, if you've dealt with vectors before, this is very familiar, right? Not new things that you've done at all. What do you get in the next one then?
4, 0, negative 12 minus negative 4, 2, 2, 5.
Okay, so distribute that negative 4, basically distribute it through, right? Multiply by each component. So you said 4, 0, negative 12, negative 12. Okay. And then we're going to subtract. What are we going to get?
8, negative 2, negative 14,
Good. Any questions on that one at all? It's really not that bad, because another reason why I think it's not too that bad is we've been doing this all semester anyway. We've been adding matrices, haven't we? Adding, subtracting, doing scale. It's the same concept, right? And we've even talked about thinking of our vectors as being a column vector, right? And think of that as a column matrix. So I'll leave the next one for you for practice if you need it. My guess is most of you are picking up on what's going on anyway, so I'll go ahead and leave that one. All right. This next page is a long page with a lot of blanks. I've got 10 blanks there, right? So there's a reason why we've got 10 blanks in here. We're going to abstract things for vectors. Basically, a vector can be anything. You're used to thinking of vectors as being ordered tuples. But another way to think about something of being a vector might be helpful is maybe as functions. You do that in differential equations, for example. You don't ever necessarily call it that, but your vectors in differential equations end up being functions when you do solutions to differential equations. Okay, so it's very helpful to abstract the notion of what we mean by a vector. So a vector might be a function. A vector might be a polynomial, in particular. A vector might be sines or cosines. If you have done any type of, hopefully we'll have time to do it this semester, I don't know if we will or not. But if you've done any type of approximations, for example, if you've done least squares, you try to approximate something with a straight line, right? Another thing to try to approximate with is functions that are modeling things that are periodic. And what I mean by is goes up and down kind of thing. So something that might be periodic in physics is turning a switch on and off. Maybe a switch goes on, switch goes off, switch goes on, switch goes off. That's hard to model because there's a discontinuity, right? Instantly it goes from on to off. But a lot of times when you want to model things, you want to model it with continuous functions. So a way to do that is with what's called Fourier series, modeling it with sines and cosines. In that case, when you're doing the modeling, you want your sines and cosines to be your vectors to do those kind of operations that we're talking about. So there are lots of instances where we're going to want to abstract the idea of what we mean by a vector. But we want all things that we're calling vector spaces, this is what we're going to talk about in the next section, we want them all to satisfy a certain set of what we refer to as axioms, certain set of properties that they must all have. I can use anything I want for a vector. I can define addition however I want. I can define scalar multiplication however I want. But scalar multiplication and addition have to behave nicely. And so what this list of properties that we're going to put here and show that Euclidean n space satisfies are kind of our agreement that this is well-behaved addition and scalar multiplication. Okay, so that's why we're going to go through it kind of painstakingly, but it's to set things up for later. Okay. All right. So let's say we have 3 vectors, u, v, and w, and c and d be scalars. Well, the first thing, hopefully is fairly obvious, is that if I take my u and I add it to v, I end up back in my Euclidean n space again. So that little, if you're not familiar with it, this just means is an element of. So I'm starting with u and v being vectors in Rn. I'm just saying when I add them together, I get back in Rn again. It's pretty obvious by the way we defined addition that this works, right? Rn is your set of n tuples. Everything in your tuple is a real number. Every component of your tuple is a real number. I add 2 real numbers together, I get a real number, and I didn't lengthen or shorten my vector dimensions at all. This is called closure under addition. It just says that when I add 2 things back together, I land back in the same place. To give you an example of something that is not closed, start with the integers and think division. If I divide any 2 integers, any 2 whole numbers together, do I always end up with another integer? No. 1 divided by 2, for example, right, gives you a half. Okay? So that's an example of an operation that's not closed in the set. Okay? I start with 2 integers. I don't necessarily end up with another integer. Okay. Right. The next few are just properties of addition that it shouldn't be a huge surprise. Oops. This just says that we can add in either order. One of the things that we'll want to do for abstract vector spaces in the next section is prove these properties are actually satisfied. So to do that in this case, this one's not too bad to prove. I want to start with u plus v and end with v plus w, or v plus u. I don't know why I keep saying w. All right, so if I want to take our x1 out to xn and add it to y1 out to yn, what do I get? Yeah, exactly right, right? If I add the x1 out to xn and the y1 out to y, add the y1 out to yn, I just add the components, right? Now remember, what are we trying to prove? That we really can flip it around. But what kind of objects are the x1 and y1? Real numbers, and this plus sign right here really does mean real number addition, right? So what can I do in each component? Flip it, yeah. I can just rewrite it as y1 plus x1, y2 plus x2, and so on down the line. Which I can just split back apart. That first vector now is the vector v. The second vector is the vector u. So we really do get commutativity of vector addition here. That was not a very difficult proof, but this is what you would need to do to show that this property is actually satisfied, right? Do your operation, get the answer. And you could have done a meet in the middle approach, right? We went from left to right, but I could have also done the operation one direction, get the answer, do the operation in the other direction, get the answer, and then argue why they had to be equal to each other. That's another way to do it. Again, the only reason why I'm doing this one, because this one I hope is obvious, the only reason why I'm doing this is because we're going to have non-obvious vector spaces, and we'll only make sure we can prove these things. Okay. All right. Next one here, and I'm not going to go through a bunch of these. I'm just going to go through. I'm going to list out what the properties are. I'm just not going to do a bunch of proofs. All right. The next one is an associativity property. You would prove it in a similar way. You would look at the left-hand side. You would add V and W together first, then add U. And you'll see a grouping in your real numbers where the second two are grouped together, but it's addition of real numbers, so you can regroup and group the first two together and then just split it back apart again. It's pretty much the same proof as what we just did. All right. This is one that students love to struggle with, not necessarily for real Euclidean spaces, but when we have weirder vector spaces. When it must be a vector that we call the zero vector in Rn, such that when I take U plus 0, I get U back again. I get 0 plus U. Now, this says there exists a zero vector. What is the zero vector in Rn? All zeros, right? That is the zero vector in Rn. Generally speaking, though, the zero vector is dependent upon how you define addition. Okay? So let's say you're weird and you decided, I'm going to define vector addition by multiplication. Then what's your zero vector in that case? Not any number. What's the zero vector? It's ones, yeah. If I decided that when I say I'm adding two vectors together, I'm really going to multiply the components, then my zero vector would be the vector with all ones in it. It depends on how we define what the addition is. You're used to defining addition as just regular old addition, right? And so you use zeros. But if you define it a different way, it might be a different vector. Or if you define it in a different way, it may not work, and you don't have a zero vector, and so then it's not a vector space. Anyway, we refer to this as the additive identity property. And remember, again, one of the reasons why, you're so used to doing things with zero, it becomes obvious of what you're doing. But remember, the whole reason why we need an additive identity, remember where algebra gets its roots. Algebra gets its roots from finding roots, solving equations. Okay? When you solve an equation, something like x plus 3 equals 7, I have to be able to undo this 3, right? Agreed? Yeah? Technically speaking, I'm going to add the opposite. I'm going to talk about inverses here in a second. But notice, when I do this, my negative 3 isn't in the right spot to cancel off the 3, right? So notice you actually have to associate, or reassociate, I should say, right? And then what does this actually equal? 0, right? So I still have x plus 0 equals 4, right? And now I need that additive identity property to be able to get to the end. Okay? This is what, again, you're used to dealing with 0. We say things that seem like they're obvious about 0, but it's not all that obvious, right? I have to have the property to be able to solve this equation. Okay? And mentioned this last semester with the students I had in abstract algebra. This is the reason why algebra is hard for kids. There's a lot of stuff going on just to solve an equation like x plus 3 equals 7. Right? There's a lot of stuff going on in there. Even though it's just something that you're used to doing for several years, and you're like, well, sure, it's 4. I don't have to do anything. Right? There's a lot of stuff going on in the background. All right. Anyway, I'll get off my soapbox for that part. Okay. All right. We have a zero vector. Again, the zero vector part is to help us do something like this. To get to that zero vector part, I needed to have inverses to get to the 0, right? The whole reason why we added -3 is because I had a positive 3 that I need to get rid of, right? So what this says is that for each vector u in Rn, there exists a vector we'll call -u, also in Rn, such that u plus -u is the same thing as -u plus u gives me back to 0 again. I have to be able to, basically all this says is that I have to be able to undo addition. Which you're used to doing when you solve equations, right? I need to be able to undo whatever the addition was. That's all that says. Now, in Rn, what is the additive inverse for any vector? What do you do to the vector to create its additive inverse? What do you do with the components? Yeah, just multiply them all by -1, right? Flip them all around, right? Flip the signs. Yeah, exactly right. But again, that's dependent upon what the addition is, how it's defined. Okay. Again, if you defined addition as multiplication, what would you use for the additive inverse? If you defined addition as multiplication, what would you use as the additive inverse in that case? I'm using air quotes on purpose. The reciprocal, exactly. That's exactly right. Yep. Because we need to notice in that case you use the reciprocal because what did you say the 0 had to be? 1. So you're trying to get back to 1 rather than trying to get back to 0. So you use the reciprocal in that case. Okay. We're gonna do more. We're gonna do examples of that next, and then the next time when we go through it. So anyway, I'm just trying to mention it for what we care about. All right. So those are the axioms. By the way, this is the additive inverse property. I'm labeling these because we're going to come back to these next time when we go to abstract vector spaces. Those are the 5 that deal with addition specifically. The next talk about scalar multiplication, and then also how some of them have how scalar multiplication behaves nicely with addition. So the first one is just the closure property again. If I take a scalar times a vector, I get back in Rn again. So this is closure of scalar multiplication. The next 2 talk about how scalar multiplication behaves nicely with addition. These really are saying 2 different things. This says that scalar multiplication distributes over vector sums because this is adding 2 vectors together. This one says that scalar multiplication distributes over what kind of sum here? Is this a vector sum? That's a scalar. It's a real number sum, right? Okay. So there's different things going on, and notice that really the second one, there's something going on. What I mean by that is this is regular old. I'm adding 2 numbers together. What does that plus sign mean? I'm adding 2 vectors together. Abstractly, there's something going on there. I'm changing my addition to different places. Okay? So you have to be mindful of that. There really is something algebraically going on here. Both of these together we refer to as distributive properties. The next one is a kind of an associativity property. But again, something is going on here. Notice on the left-hand side, what kind of objects am I multiplying together here? A scalar and a vector, right? And then get a vector and then do the same thing again. What kind of objects am I multiplying together here inside the parentheses on the right side? Real numbers. So that multiplication is not scalar multiplication. It's literally real number multiplication, right? So again, algebraically, something is going on there. Okay? And we really do talk about this as associativity. Oops. And then the last thing is a scale. Remember we talked about how we had to have a scale for determinants? If we talk about scalar multiplication, there must be some scale going on, right? If I take 1 and multiply by a vector, I just end up with a vector back again. Your book refers to it as a multiplicative identity property. But in particular, it just says that I take 1 times a vector, I have to get the vector back again. There's a name for that algebraically if you go farther along in abstract algebra stuff that I'm not going to mention. Yeah. Okay. All right. So anyway, like I said, these are properties that any vector space has to have based on the way that we define addition and scalar multiplication. Turns out that Euclidean space satisfies all those because we've defined our addition and our scalar multiplication in the obvious way, and really all we're doing is using properties of real numbers. So what we'll see when we talk about abstract vector spaces that we'll be changing things up, we'll actually have some things to prove. Okay. All right. You've already mentioned this before, but let's go ahead and write it down. In Rn, what do we use for the additive identity? What vector do we use? Yeah, all zeros, right? So we would use the vector that just has a whole bunch of zeros in it. Right? That's the 0 vector. If I have the vector v that's made up of x1, x2 out to xn, you just told me a minute ago what we use for the additive inverse. What do you do with all the components? Yeah, make them all. Yeah, just take them all negative. Take the negatives of each of them, right? All right. So some of the properties that actually work for any vector space, and I'm going to prove it that way rather than proving it specifically for Rn's, are the next 5 properties that we have here. The first one says that the additive identity is unique. I'm going to go through this proof because it illustrates how we show things are unique, and I think I've mentioned this before when we did uniqueness of inverses of matrices. Remember, when we want to prove something is unique in math, we assume we have 2 and show they're equal. Okay. So let's suppose that we have 0 and 0 prime are additive identities. Now, again, this says that it's in Rn. Oops, I can spell. But we're gonna prove this so that it works for any vector space. So we don't have to reprove it again. Okay. I'm going to write this in the middle because I'm going to go left one way and right the other. Okay. Okay. I'm going to start with this. All right. If I take the 0 vector and add it to any other vector, if I said this was a u instead, If I take the 0 vector and add it to u, what do I end up with? The u, right? So on the one hand, this would equal 0 prime, right? Because adding by 0 doesn't change anything, correct? Okay. All right, now do it the other way around. If 0 prime is your additive identity, and I think if this is my u, what do I end up with? The u again, right? So on the other hand, this has to equal just 0. Now, did I show those two things are equal to each other? Yeah. Okay. That's it. That's the whole proof.
So it depends on what comes first.
No. Nope, doesn't matter. This one is because 0 is an additive identity. Oops. That's the right identity. This way is because 0 prime is an identity. We're saying they're both identities, so they both have to act like identities. So going the right direction is because 0 is an identity. Go to the left direction is because 0 prime is an identity. So they are equal to each other. That's the whole proof. It was very exciting, wasn't it? Okay. The second one says that the additive inverse of a vector, oh my heavens, is also unique. Again, you'd prove it the same way. Assume you have 2. Assume you have 2. Show that they have to be the same. Okay. It's the same type of proof, so that'll be a good one to practice with. See if you can do it. Okay. The third one, you've probably always been taught all your life that 0 times anything is 0, but you probably never proved it necessarily, right? Okay. We're going to prove one of these. This says that if I did, by the way, this is kind of there's lots of things in math that you can switch around, and something that you think is true in one spot isn't necessarily true in another. For example, all your life you grew up saying multiplication I can do in either order, and then you get to matrix multiplication. Can you do it in either order? No. Okay. This is a pretty universal truth in math, that if you take whatever you're calling 0 and multiply it by something, you end up with 0. Okay. In my thesis, when I was for my PhD writing my dissertation, there was a structure that I dealt with where 1 times 1 was equal to 2. So even that didn't hold, right? But again, pretty universal. If I do 0 times something, I get 0. Yeah, it was a structure where 1 times 1 is equal to 2. It was weird. I'm not saying it's not weird. I'm just saying that it happens. All right. In any event, let's talk about how we prove this. Math is fun. I love it. Change things up, something else completely different might come back out again. I love it. That's why I've started studying it. All right, can't get enough of it. All right. This is also a pretty good trick that you do in math. You just cleverly rewrite 0 and see what happens. Okay? In this case, our clever rewriting of 0 is, I'm going to write 0 as 0 plus 0. That is the number 0, right? By the way, this is the real number 0, not the vector 0. Okay. But now what can I do on the right-hand side that I couldn't do before? I can distribute, right? And now if I want to make one of these go away on the right-hand side, I can add the inverse. Right? Just added I know that the inverse exists, right? So I can add it. Now I need to reassociate so I can get back to 0.
The inverse is negative.
Hmm?
The inverse is a negative.
Remember, our notation uses a negative sign, but it literally is the additive inverse. Okay, so it's the thing that gets me back to 0. Now, usually you would write a minus, but that's just writing it as the additive inverse here. Oops, forgot the plus sign. And then the thing in parentheses now is also the zero vector. And when we add the zero vector, I get the zero vector. It was a lot of work to prove that, wasn't it? Okay. I'm going to go back through it. Okay. So let's look at this. What did we do? Well, the first thing I just used the fact that I could rewrite the number 0 as 0 plus itself, right? But notice here I had to use one of the axioms of our vector space. I had to distribute, didn't I? To get to this step. That was axiom 7, I think, is what we had listed up there before. It was 7 or 8. I think it was 7. It was one of the. I think it was a 7, right? Because it was a single scalar and 2 vectors. Oh, it was 8. You're right. That's 8. That's 2 scalars and a vector. Thank you. All right. Then what axiom did I use? What did I do? What property did I use here to go from that step to that step? Additive inverse. That's 5, right? Okay. But notice I'm adding the additive inverse to both sides. This is still in parentheses over here, right? Because I'm adding that vector to this whole thing. What did we use next? Associative. That was axiom 3, right? Okay. Then this is axiom 5 again, because when I add the additive inverse, I get 0. It's the whole point, right? I also used it over here. And then if I add 0 to anything, I get the vector back again. That was axiom 4. A lot of axioms in there to prove that, right? Yes. Mm-hmm. That's property 5 because I'm adding a vector and its additive inverse. That's property 5. Okay. By the way, the proof works exactly the same way. If you take any scalar and multiply it by the 0 vector and get the 0 vector back out, you should be able to mimic that proof and get the proof for number 4. Again, it'd be a good one for practice. Don't be surprised if one of these things shows up on your next test, by the way.
Thank you.
Yeah, you're welcome. Yes.
So in the properties, when it says U vector, the U represents any number.
The U represents any vector, yeah. Yep. Every single vector has to have an additive inverse. And then 5 says, well, it's like a 0 factor property. Oops. You should have an if in front of this. If I take a scalar times a vector and get the 0 vector, then what do you think you can say? The scalar is 0 or the vector is the 0 vector. Yep. That one's also a good one for a practice proof. I know that if C is equal to 0, then I get that anyway, right? So a good practice proof for this would be to suppose that C is not 0 and prove that V has to be 0. That's a good practice. Okay. Okay. And then the last one says that if I do the additive inverse of the additive inverse, what better I get? Better get the V back again, right? This has to do with being unique, right? Okay. So this has to do with being unique. All right. We'll leave there's just one last little thing that we have to do to finish this off. Okay. We'll finish that up next time just because we got about 1 minute and I'm not going to be able to. It's going to take like 5 minutes. It's not going to take very long. But I'm not going to keep you 5 minutes late. So have a good weekend. We will see you on Monday.